Welcome to ElectrAspirant, an assistance to electrical students for objective type exam preparation. It's an initiative of Department of Electrical and Electronics Engineering, Christ College of Engineering, Irinjalakuda. In this presentation, I will discuss some numerical problems in control system subject under the topic time domain analysis. The prerequisites are time domain specifications, transient and steady state responses, steady state error analysis, Routh stability criterion, and root locus. Coming to the first question, in the feedback system given below, g of s equal to 1 by s square plus 2s. The step response of closed loop system should have minimum settling time and have no overshoot. Then the required value of k. Now for the given question, it is very clear that it is a second order system. Now we can obtain the closed loop transfer function as y of s by r of s equal to k divided by s square plus 2s plus k. Now by comparing with the standard closed loop transfer function of second order system, it is omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now as per the given question, the system response should be minimum settling time and have no overshoot. It happens when theta equal to 1, that is for the critically damped case. Now when theta equal to 1, then by comparing the coefficient of the 2s, we get omega n equal to 1. Now we know from the expression it is very clear that k equal to omega n square, so it is equal to 1. So the answer is k equal to 1. Now coming to the second question. For the unity feedback system shown in figure, the open loop transfer function g of s is 2 by s into s plus 1. The steady state error due to unit step input is. Now since the input is a unit step, the steady state error is given by means of an expression ESS equal to 1 divided by 1 plus Kp, where Kp is the static position error constant and it is defined as limit s tends to 0, the open loop transfer function. Now from the given system, the open loop transfer function is 2 divided by s into s plus 1, hence Kp become infinity, hence the steady state error become 1 by 1 plus infinity, it is equal to 0, so the answer is A. Now coming to the third question. A closed loop system has the characteristic equation given by s cube plus k s square plus k plus 2 into s plus 3 equal to 0. The system to be stable, which one of the following conditions should be satisfied? Now since we have the characteristic equation, we can obtain the Routh array like this. That is, we can form the Routh array like this. Now we know the system will be stable only if the first column of the Routh array element should be all having the same sign, or in this case all should be positive. Now it happens when the term k should be greater than 0 and this term should be greater than 0. So k square plus 2k minus 3 will be greater than 0 if only if k is greater than 1. So the answer become option D. Okay, now coming to the next question. The value of A0 will ensure that the polynomial s cube plus 3s square plus 2s plus A0 has roots on the left half of S plane. It is again a problem related to Routh stability criterion. So first of all we can form the Routh array like this. And we know the system will be stable if all the roots are on LHS of S plane. And if the first column of Routh array is all having the same sign, then all the roots will be on the LHS of S plane. That is, here the terms 6 minus a0 by 3 and a0 should be positive. Then only all the roots will be on LHS of S plane. That is, a0 should be a positive value. Now 6 minus a0 should be greater than 0 only if a0 equal to 5. As per the given options, the apt answer is a0 equal to 5. That is, answer is D. Coming to the next question. The open-loop transfer function of a unity feedback control system is g of s equal to k divided by s square plus 5s plus 5. The value of k at the breakaway point of the feedback control system's root locus plot is. So it is related to a problem from root locus and a breakaway point of root locus. Now, since we have the open loop transfer function, we are able to form the characteristic equation as 1 plus g of s h of s equal to 0. As per the given problem, it becomes s square plus 5s plus 5 plus k equal to 0. Now, to get to the breakaway point, we know we need to find a dk by ds equal to 0. dk by ds equal to 0, then we can find from the expression we have k equal to minus s square minus 5s minus 5. Now by taking the differential, we can solve that the breakaway happens at s equal to minus 2.5. Now calculate the Cart's equation at s equal to minus 2.5. We will get the value of k as plus 1.25. So the answer is k equal to 1.25. Okay, now coming to the next question. The forward path transfer function and the feedback path transfer function of a single loop negative feedback control system is given as g of s equal to k into s plus 2 divided by s square plus 2s plus 2 and h of s equal to 1. Okay, so here g of s, it is the forward path transfer function and h of s is the feedback path transfer function given. Now it is in connection with the breakaway point and root locus again. Now we know to get the Cart's equations 1 plus g of s into h of s equal to 0, you can form the expression and we need to find an expression for k. Then go for the differential dk by ds equal to 0. Then thereby you can find the location where the breakaway happens and you can find it as s equal to minus 3.4. That is the breakaway point. Okay, now coming to the next question. For the given polynomial s cube plus 5.5 s square plus 8.5 s plus 3 equal to 0. The number of roots of the polynomial which have real parts strictly less than minus 1 is. Again we can solve this problem by forming a Routh array and we can obtain the answer as equal to 2. There are two roots having the real parts strictly less than minus 1. Okay, now coming to the next question. The open loop transfer function of a unity feedback control system is g of s equal to k into s plus 1 divided by s into 1 plus ts into 1 plus 2s with k greater than 0 and t greater than 0. The closed loop system will be stable if, again, the stability we can form by using the characteristic equation of the system. That is, we can first of all we need to form 1 plus g of s h of s equal to 0. Then we will get a polynomial in terms of k and capital T. Then by using the Routh array concept, we can find the stability condition and you will get the condition as option C. That is 0 less than k less than t plus 2 by t minus 2. Coming to the next question. The open loop transfer function of a unity feedback control system is given by g of s equal to k divided by s into s plus 2. For the peak overshoot of the closed loop system to a unit step input to be 10%, the value of k is. Okay. Now the given transfer function, it is a second order system. you can form the closed loop transfer function as g of s by 1 plus g of s h of s. Here h of s is unity. So you can obtain the standard second order transfer function. You have to equate with that. Then we can find you can see that k equal to omega n square. Okay. Now the another data is given is for the peak overshoot of closed loop system to be unit step input to be 10%. We know the peak overshoot expression is given as e raised to minus theta pi by root of 1 minus theta square. It is equated with 0.1. From that we can obtain the value of zeta, that is the damping ratio. Now by comparing with the closed loop transfer function, we can find the value of omega n. Thereby we will get the value of k equal to omega n square, and it has 2.85. Okay, now coming to the last question. The first two rows in a Routh table for a classification is given. The range of k for which the system is stable. Again we can complete the Routh array. Then by observing the first column of Routh array, that is in order to system to be stable, we can obtain the condition as the option D, that is 0.5 less than k less than infinity. Okay, thank you for listening. Thanks.